Good morning. We are going to discuss 13.4, and in 13.4 we discuss the Haworth structures. And here we are discussing how to set up a Haworth structure for a monosaccharide. And as you can see, the most stable forms of pentose and hexose sugars are 5 and 6. So Haworth structures are ring structures. That's the first point. The second point is they are very stable. These rings, known as Haworth structures, are produced from a reaction of the carbonyl group and a hydroxyl group in the same molecule. So these pentose and hexose sugars have 5 and 6 carbon atoms respectively. So the carbonyl group, the aldehyde group, the carbonyl group, and one of the hydroxyl group, hydroxyl is the OH, one of the OH and the carbonyl group in the same molecule come together to create a ring structure called the Haworth structure. And in this unit, we are going to draw and identify the Haworth structures of monosaccharides. So let us look at what are the guidelines to set up a Haworth structure. Step 1 is turn the Fisher projection clockwise by 90 degrees. Fold the horizontal carbon chain into a hexagon and bond the oxygen on carbon 5 to the carbonyl group. Draw the new OH group on carbon 1 below the ring to give an alpha isomer, or above the ring to give a beta isomer. So let us take an example. So this is our Fisher projection. And this is 1, 2, 3, 4, 5, 6, a 6 carbon glucose. And this is D-glucose. The OH is to the right. So we are turning the Fisher projection 90 degrees clockwise. So here, horizontal. So this is the first step in setting up a Haworth structure. Turn the Fisher projection clockwise. Fold the clockwise horizontal Fisher projection to make a hexagon. So we are folding the structure, and this oxygen of the OH in carbon 5 and the carbon in the carbonyl group, carbon 1, we are connecting the two. So now the hydroxyl group that is created by the connecting is either up, above, or below. So these are two important points to remember. Now we are folding the horizontal structure, and we are making a hexagon out of it. So the carbon 5 oxygen bonds to carbonyl. Carbon 5 oxygen bonds to carbonyl. So this hydrogen connects here. So once we set up, it becomes a cyclic structure. So this is carbon 1, 2, 3, 4, 5, 6, and the oxygen is bonding to carbon 1. The hydrogen of the hydroxyl is located here. So this is now a cyclic structure. So now again, place the carbon 6 in the CH2OH group above carbon 5. So now carbon 6, this carbon is here. Draw a bond between the oxygen of the hydroxyl in carbon 5 to the carbon in carbonyl group. So this is how we set up a Haworth structure. So now once we set up the structure, the OH group can either be above or below the ring. So when the OH is below the ring, you have an alpha isomer. When the OH is above the ring, you have a beta isomer. And both are D-glucose because of the arrangement here. The OH on carbon 4 is to the right. OH. So these are D isomers. The alpha is when the OH in carbon 1 is below the ring. Beta when the OH in carbon 1 is above the ring. So alpha D glucose, beta D glucose, and these are the Haworth structures. Now, when we have a solution of glucose, in a solution, there is mutarotation. What is mutarotation? The alpha D glucose in a solution, now this moves into or converts into an open chain structure briefly, and then goes back into a cyclic form, giving the beta isomer. So there is a rotation between the alpha and the beta when you have a glucose solution. So when placed in solution, cyclic structures open and close. Alpha D glucose converts to beta D glucose and vice versa. At any time, only a small amount of open chain forms. You have a small amount of open chain, a trace amount. You have a certain percent of alpha isomer and beta isomer present in a solution. So that is mutarotation. They rotate between the two, alpha and beta, in a solution. Now we are talking about the Haworth structure of fructose, and fructose, if you remember, is a ketose. There is a keto group on carbon 2. This is D-fructose. Again, the OH on carbon 5 is to the right, D-fructose. And we identify fructose carbonyl on second carbon. Now the same, it is a ketohexose, forms a 5-carbon ring structure with carbon 2 forms when the OH group on carbon 5 reacts with carbon 2 in the carbonyl group. So now we are going to rotate and bend clockwise and connect the ring. So now we are turning the ring again. The 6th carbon, CH2OH, is here. The oxygen from the OH in carbon 5 connects to the carbon 2. The carbonyl group is in carbon 2. So it connects, and CH2OH, the carbon 1, alpha D fructose. Here, beta D fructose. Alpha below, beta above. D fructose is because of this hydroxyl group to the right. Alpha below the ring, beta above the ring. Here again, the difference is carbon 2 is the carbonyl group. So carbon 5 is connecting to carbon 2. Okay? So this is the Haworth structure for fructose. Again, the same guidelines. Turn clockwise, bend to connect carbon 5 hydroxyl to the carbonyl carbon. In aldose or glucose, the carbonyl carbon is carbon 1. In fructose, the carbonyl carbon is carbon 2. And the alpha and the beta isomer are due to the position of the hydroxyl group in carbon 1. Below the ring is alpha, above the ring is beta. So now we are going to set up the cyclic form of D-galactose. So let me check, okay. So this is D-galactose. This is the aldose, we can see aldehyde. And this is the only difference between D-glucose and D-galactose is the OH in carbon 4 is on to the left. In glucose, the OH is to the right. So D-galactose, D, OH, carbon 5 to the right. So let us set up the cyclic structure. So now we are going to, step 1, turn the Fisher projection of galactose horizontal, 90 degree. Okay. Then turn, fold clockwise to make a hexagon and bond the oxygen of carbon 5 to the carbonyl group. We're going to turn it in and then make a hexagon, and the oxygen of carbon 5 hydroxyl group connects to the carbonyl carbon, and the hydrogen connects to the oxygen to create a hydroxyl group. Now write the hydroxyl group on carbon 2 below the ring, and the hydroxyl on carbon 3 and carbon 4 are above the ring. These are talking about these hydroxyl groups. This is about these hydroxyl groups. The CH2OH carbon 1 is located here. Now this oxygen connects on, this hydroxyl is on carbon 5. The oxygen connects to carbon 1. Now if the hydroxyl group in the cyclic structure is below the ring, you have alpha D-galactose. If the hydroxyl group is above the ring, you have beta D-galactose. So draw the new OH group on carbon 1 below the ring to give the alpha isomer, or above the ring to give the beta isomer. So this is how you set up a Haworth structure.